Okay, hi everybody. So I'm going to be talking about the Nernst equation and pH. So this is going to primarily focus on the LBLA questions 8 and 9, but I'm also going to give you some hints for the expo for that table because a lot of people are having issues with that as well. So the first thing that I want to point out here is that H2SO4 is a strong acid. And that means that even though this says it's H2SO4, the better way to think about this is that it's 2H plus 2HSO4 minus. And that's because a strong acid typically dissociates completely when it's in water. The second dissociation for this molecule here is very complex, so we're going to pretend that it doesn't happen, which is why for question 7 on the LBLA, you were supposed to say that it was in primarily this form because this will dissociate and you will not hit the next step. So with that being said, I want to talk about question 8 now. Or question 9, sorry, that was for question 8. So this question is asking what the pH must be for to hit E cell or its standard cell potential E naught equals 2.05 V. And the thing that's important to take home here for question 9 is that this happens at equilibrium. And we know this because right above it says that that's the standard, which happens at equilibrium. So you have an equation that is E equals E naught minus RT over NF ln Q. So with that being said, if this is going to be equal to 2.05 and this is equal to 2.05 minus these are going to cancel and you're going to be left that 0 is equal to this, which means that this value here is going to be 0 or has to be 0. So one thing that you should know is that the natural log of something equals 0 is 1. And I'm just going to verify that. Yes, the natural log of 1 equals 0. So from that, we can say Q has to equal 1 because we need this to be equal to 0. And this makes it so you can solve for concentrations. So I'm going to erase this. And I'm going to say, okay, so we know that Q needs to be equal to 1. And we want to find concentrations. So I'm going to write Q out. And Q is equal to products over reactants, which is going to be equal to a big equation. So I'm going to write this out. And I'm going to account for the stoichiometry. And the one thing I am going to do, though, is write this H2SO4 in this form because it will make my end goal of finding the pH a little bit easier. So one thing that you should note is that solids and water are assumed to have a concentration of 1. So with that being said, we know that this is a solid, this is a solid, this is a solid, and this is a solid, which means that this, and this all go to 1, which leaves our Q, so it leaves us with the situation of Q equals 1, and it equals to 1 over H squared times HSO4 squared. So with this, you should be able to manipulate this to solve for H very quickly. This is going to be 1 equals H squared, HSO4 squared. If this was a little bit more complicated, you could do an ICE table, but this is pretty straightforward because we know that these are the same ratio. So this is really equal to 1 equals x to the 4th, and solving for x is going to be equal to 1, which means that your H plus concentration is 1. So if we know that pH is equal to the negative log, if we know that pH equals negative log H, and we know that H is 1, we have negative log 1, which leaves our pH equal to 0 because the log of 1 is 0. So that's how you solve for that. But if you weren't at equilibrium and you had, say, what the potential was, like in the activity, and you have the concentration of HSO4, you could figure out what the cell potential is because you have the Nernst equation. So if you do oxidation numbers to this type of equation and you have that E equals E naught minus 0.0592 over N. And if you don't know that this is the same as RT over F. So it's just an easier way to write it. ln Q. This is also sometimes ln K depending if you're not at equilibrium. But if you have, the standard potential is 2.05, and you can figure out how many electrons are transferred so you can fill this in. And if you know concentrations, you should be able to manipulate Q in the same exact manner to figure out what this would be. So that's how you would go about using Nernst equation to relate to pH and concentration, by expanding this Q to be products over reactants raised to their stoichiometric coefficients. So I hope that this was helpful. If not, please leave a comment below or post a question on Piazza. Okay, thank you.